So here's the first new thing about random variables that's different from random events, and it's the probability mass function. So associated with each of the values x that a random variable can take, remember they're just numbers, there's a probability, the probability that x equals x. And if we just list, because if they're a discrete random variable, we can just list all the possible values and their probabilities, and that is the probability mass function. So for example, if our random variable is the number of heads from 2 coin flips, the probability we get is 0. The probability x equals 0 is that we get no heads, is the probability of the event 2 tails, which is a quarter. Probability x equals 1 is a half, it's the event that we get heads or tails or tails or heads. Probability x equals 2 is that we get 2 heads, is a quarter. That is the PMF. So just listing the set of values that x can take and their corresponding probabilities. So nothing very special about it, but it's a nice, convenient way, compact way to describe a random variable, because it includes all the values that it can take here, right? So we know all the possible values it can take and the corresponding probabilities. And so we know pretty much everything we need to know about the random variable to let us do all the calculations. So it's a nice way to summarize a random variable. So here's another example. If we look at the sum of 2 dice, so that's going to be take values 2, 3, 4, 5, 6 and so on. Then the probability that x equals 2, that's our random variable x is the sum of 2 dice, is that we had the probability event that we threw 2 1s, that's 1 over 36. Probability x equals 3 is that we had a 1 and a 2 or a 2 and a 1, so that's probability 2 over 36. Probability x equals 4 is that we had a 1, a 3, 2 and 2s, or a 3 and a 1, so that's 3 over 36, and so on. And because here there's 36 of them, it's going to be quite long to write it out. And so often it's more convenient just to draw a picture, and it's easier to visualize what's going on. And so this is the kind of way you would plot a PMF. So you do it as a bar plot, and along the x-axis here is the values that x can take, so 2, 3, 4 up to 12. And on the y-axis is the probability of each of those values. So the probability of 2 is 1 over 36, which is written there. Probability of 3, x equals 3, is 2 over 36, then 3 over 36, and so on, and it peaks in the middle, and then heads back down again. And we draw it as bars because if you drew a line joining these, that would be incorrect, because there's no idea of continuity or smoothness here. These could jump around all over the place. Instead, we're just drawing bars to capture the discreteness of the data. But it makes it easy to see what's going on. You can see the set of values around the variable can take, the different probabilities, and so it's nice and convenient. Now there's a second quantity that's actually more, it seems less obvious, but actually is more fundamental, and that's the cumulative distribution function. And it's defined as the probability that a random variable x is less than or equal to a, where a is a parameter. And we call that f of a. So that's now a function. So as a varies, and remember so it can be a real number, it can vary all the way from minus infinity to plus infinity, it's all well defined. We can calculate the probability x is less than or equal to a, that's well defined, that's just a number. And so this is a function of a, that's what the CDF is. But when it's a discrete random variable, the CDF only changes for the values where x changes, the values x can take. So suppose we've got a random variable that takes values x1 through to xn. Then the probability that x is less than or equal to a, what you do is you sum up over all the values of xi less than or equal to a. So for example, if you're interested in the probability, f of, so let's look at the sum of 2 dice maybe, that would just be, look at this graph here. So here the x-axis is a, here the y-axis is the CDF, and this, remember the PMF from the previous slide, this is just the corresponding cumulative distribution function. So the probability that x is less than or equal to 2 is just 1 over 36, right? Same as the probability that x equals 2. Probability x is less than or equal to 3, well, it's the probability that it's equal to 2 or equal to 3. So it's a bit higher, so it's 1 over 36 plus 2 over 36, is there a value there? And so on. So the probability, the f of 4, which is probability x is less than or equal to 4, is probability x equals 2 or 3 or 4. And so what you do is you sum over all the values of x less than or equal to a, all those probabilities. And because of that, the CDF has always has the same kind of behaviors, in that in the left hand side here it always starts at 0, so the probability that x is less than or equal to 1, for example, is 0, right? Because x has to be 2 or more. So the CDF at the left hand side here, if you make it small, choose the a small enough, it will always be 0. And equally, if you choose the a big enough, it will always end up at 1. So the probability x is less than or equal to 20 is always equal to 1 when it's the sum of two dice, right? Because the maximum it could be is 12, so of course it's always less than or equal to 20, or less than or equal to 12 in fact. Eventually it will hit 1. So it starts at 0, it goes to 1, and it always increases because we're always increasing the number of events that we're covering. And so often you have this kind of S-shaped where it starts off shallow as a steeper bit and then becomes smooth, shallower again. It doesn't necessarily have to have that shape, but what it does do is have to start at 0, end at 1, and always be increasing. That's how the CDFs look. So let's look at an example. So let's just pick an artificial one, right? So if the probability x equals x is equal to x over 10, right? Just pick something out of the air. What's the CDF? And x can take the values 0, 1, 2, 3, 4. So the probability x is less than 1 is the probability that x equals 0. So the probability for x less than 1, the CDF of x is just the probability x equals 0, which is 0. For x here between 1 and 2, the f of x, so I've flipped from a to using x here. F of x, so the probability that our big X here is less than or equal to this little x, and Sx is in the range 1 to 2, is the same as the probability that x equals 0 plus x equals 1. So x equals 0 or x equals 1. Which is 1 over 10. X equals 0 is 0. Then we add x equals 1 is 1 over 10. So we get 1 over 10. And then when x here is between 2 and 3, our CDF is the probability that the big X is less than or equal to f. It's just going to be the probability x equals 0 plus x equals 1 plus x equals 2. So you see you get the interesting values here are correspond, so the 1, the 2 and 3 correspond to the values that x can take. And what we do is we sum over all those values that are less than that to get the probabilities, to get the CDF. And so we can write out the CDF in this case in this way. So that's just summarizing what our calculation there. And we can flip back and forth between CDFs and PMFs in quite a straightforward way. So let's look at that. Well, we've already seen how we can map from the PMF to the CDF, right? So the CDF only changes values at 0, 1, 2, 3, 4. Then that tells you that the X only takes values 0, 1, 2, 3, 4. So we know the set of values X can take by spotting the values where the CDF changes. Now we know, suppose we're given a CDF, so the task here is given a CDF, extract what the PMF is, right? So suppose we're given that f of 0 is 0, then we know that the probability x equals 0 is 0, right? And we're told f of 1 is 1 over 10. And so that's going to be the probability of x0 plus x1. Now we know x0 is equal to 0 from our f0. So that means probability of x equals 1 is equal to 1 over 10. So what we're doing is substituting what we found from earlier stages back in. So probability x is less than or equal to 2 is 3 over 10. That's from we're being told that from our CDF. We know that's equal to the probability x equals 0 plus x equals 1 plus x equals 2. So we know already probability x equals 0 is 0. We know probability x equals 1 is 1 over 10. And we know 1 over 10, so 0 plus 1 over 10 plus the probability x equals 2 is equal to 3 over 10. And that means the probability x equals 2 has to be 2 over 10. And so on. And so given the CDF, you can just substitute back values in and figure out what all the PMF values are. You can see why you need to have, it's straightforward enough algebra, but you need to be comfortable with this basic algebra to be able to do these kind of calculations. And so why do we care about them? Mainly because they're convenient ways of representing random variables. They're a nice, concise way. We can draw pictures and look at them, and they're nice and compact. And it turns out actually that the CDF is more canonical, it's more basic than the PMF. So the PMF exists for discrete random variables, but not for continuous random variables, as we'll find out later, whereas the CDF exists for all random variables. And just to wrap up, I'm always going to use just a notation, uppercase x for random uppercase letters for random variables and lowercase for values, so I've been doing that already. But just be aware when you're looking on the internet or reading in books, then there are alternatives. So for example, I'll consistently use probability x equals x, for example, just to try and be clear. It's quite common to instead write something like p sub x, sub big X, bracket little x. So what that's saying is the probability that random variable x, the random variable is given as a subscript, and the x there is the probability x equals x, is the value you're interested in. And sometimes you might even drop, where it's clear what the meaning is, you might even drop the subscript x and just write p of x. And normally you'd use capitals for discrete random variables. Sometimes people use lowercase as well, but it's normal to use capitals. And the reason to write that is them this way mainly is just to save space. Writing out p of x equals x takes a lot of space on the page. It's very clear, of course, but there's costly in space, and so these more compact ways of writing it, they're faster to write and they save space on the page. So that's why people sometimes prefer to write them that way. And you can see it maybe even more clearly when you look at giant probabilities. So the probability x equals x and x equals y is quite long to write. And so for the corresponding kind of notation you might write is pxy. So the x and the y tells us the two random variables we're interested in, that's the subscript. And then the x comma y tells us the two values we're interested in. You can see that's much more compact than writing this thing out longhand. And sometimes you might drop the x and the y where the meaning is obvious and just write pxy and save even more space. So just a heads up that the notation for describing random variables like this isn't set in stone. I'll consistently use this notation, pre-x, probability x equals x, this way. But when you're reading around, you might find other notation, so you just need to be aware of that.